Hello, welcome back. This is the next series of these videos that's going to talk about radiation detection devices. And the topic of this one is luminescent dosimeters. These are really remarkable little devices. They don't have any wires attached to them. They don't have any ionization potentials. They're just like a little chip that you can stick on a patient or even in a patient and, like, say, the oral cavity, measure dose. So there's a lot of applications for these. They're not, like diodes, they're not super accurate. They're not as accurate as ionization chambers, but you can get down to really good accuracy. So let me describe how these work, these mysterious little chips. Here we go. The first type of luminescent dosimeter I'm going to talk about is based on aluminum oxide. And so that's actually a crystal. It's grown as a crystal. And these little crystals are then embedded in a plastic matrix. And it's that device that you read out. Now, these are grown in the presence of carbon. And when you do that, this becomes light sensitive. This crystal becomes light sensitive. And so that's the first type of detector I'm going to talk about. So here's the crystal. The atoms are arranged in an orderly fashion. And it has quantum mechanical energy levels, just like you would have in an atom, but instead of being discrete single states, they're actually bands. So the electron can be anywhere in this band, the valence band, this one's called, or the electrons could be up here in a conduction band, so at a higher energy. And then there's a difference in energy between these two, which is called the band gap, which depends on the kind of crystal that you have and the doping. So if you have an electron in the valence band, could get kicks up to the conduction band if you give it energy in the form of, let's say, radiation. And these electrons in that conduction band in this particular crystal are stable. So they sit there, they remain there for some long period of time. And you stimulate it now with some light photon, let's say a laser or a LED, and then it can drop that electron down from the conduction band into the valence band, and you get a photon out at another particular energy. So the crystals we're talking about, that energy comes out at 400 nanometers, which is an optical signal, optical photon. So this is called optically stimulated luminescence, or called OSL. LD. D is dosimeter. There's another kind of crystal that's thermally stimulated, and that's called a thermal luminescent detector, or a TLD. The idea is the same, it's just a different type of crystal, lithium fluoride typically. Now, to read these out, you heat them up. So you heat them up to about 180 degrees C, and as you heat them up, the output goes up. So you can look at output versus time or temperature, and it goes up and reaches a peak and then comes down. And this is called the glow curve. And you can look at the shape of that curve and get the dose out. OSLDs have a different type of curve. So here's what an OSLD looks like. It's embedded in this little plastic holder, and you radiate the whole thing. It has a little barcode that you can keep track of which dosimeter is which. And then here's the reader on the left. There's a drawer that comes out. You put that little plastic holder in. It pulls the chip out, reads it with an LED, and puts it back in for you, and you get a dose. Now let's look at some of the advantages versus disadvantages of now looking at these luminescent dosimeters. So let's look at the pluses first. Number one, it's small, and it's compact and it's passive, meaning that it doesn't have any wires or anything like that. So that makes it very good for in vivo dosimetry. You can put it on a patient, or as I said, or in a patient cavity. It's also good for reading dose on the skin because it can get right on the surface. Another application for these is in a remote dosimetry system, for example, the mail order dosimetry check systems, and we're going to hear more about those in the lecture on QA. Second, they're very sensitive. So you can even read doses in the millirem range, very, very low. And so they're actually really good for even for doing like film badges, personnel exposures, because you can get really small doses. The ease of use is another advantage, especially these modern OSLDs and the readers. They're very designed to be user-friendly. They have minimal temperature dependence, the OSLD, minimum dose rate dependence, minimal dependence on the angle of the beam. So you'll remember that's all quite different than what it is for diodes. So this all sounds great, but let's look at the flip side. Things to be aware of, the limitations of such a detector. Like all detectors, it's not all good. So number one, there's a nonlinear dependence on the dose that this OSLD gets. And that's especially true when you get up to higher doses. It becomes superlinear and above about 2 gray. So you need to take that into account. It's not necessarily a fundamental hurdle, but it means that you have to calibrate each chip. And each chip actually varies. The response varies from chip to chip. You can buy them pre-calibrated, but you need to take it into account. Third, there's a fading that happens of the signal. So because of those traps, will kind of transition randomly, but it will stabilize after the first few minutes, and then you can read it out after that. But if you read it in the first few minutes, you will get a artificially high reading. And then there are issues with reuse. It can, in principle, be reset by illuminating it with a bright light. You can expose the OSLD and then reuse it, but that's something that's a little tricky. And then I didn't write here that these, but it should be obvious, these don't provide an immediate readout of dose. It takes a few minutes. All right, so there you go. Those are the basics of luminescent dosimeters. I'm going to leave you with a little bit more further reading if you like. Hopefully you understand these mysterious devices a little better. In the next video, we're going to talk about the next type of device, which is film. Very important. See you in the next video.